Ever hit refresh on a web page and just poof, it appears? Or maybe you've wondered how that add to cart button actually sends your order to the server. What if I told you a simple, yet incredibly powerful protocol makes all that magic happen every single second? Look, if you're building anything for the web, a front-end app, a backend API, even just dabbling with scripting, you're speaking HTTP. Knowing its ins and outs isn't some academic exercise. It's fundamental to debugging, optimizing, and truly understanding how your code interacts with the world. By the end of this video, you'll not only understand the core mechanics of HTTP requests and responses, but you'll also gain a developer's intuition for why things work or break on the web with insights that go beyond the textbook. Chapter 1. The Client-Server Dance. Let's start with the absolute basics. At its heart, HTTP is a request-response protocol. Think of it like a conversation. You, the client, probably your web browser, initiates a request. You're asking for something. Then, there's the server. This is where the website files, databases, and application logic live. It receives your request, processes it, and sends back a response. It's a very structured conversation, not just shouting into the void. Honestly, I think this fundamental interaction is often overlooked when people jump straight into frameworks. Chapter 2. Dissecting the HTTP request. Okay, so what does an HTTP request actually look like? It's not just a vague, hey, give me stuff. Every request has a few critical parts. The request line, headers, and sometimes a body. Think of it like ordering food. You specify what you want, how you want it, and sometimes extra instructions. First, the request line. This includes the HTTP method, like get for fetching data, post for sending it, the path to the resource you want, and the HTTP version. For instance, get/API/users HTTP/1.1 is asking for a list of users using HTTP version 1.1. It's concise, clear, and absolutely essential. Next, the request headers. These are key value pairs that provide extra information about the request or the client. Things like user agent tells the server what browser you're using, accept tells it what kind of data you prefer, and host specifies the server. Hot take. Content type is probably the most misunderstood header for beginners. Finally, the request body. Not all requests have one. You typically include a body when you're sending data to the server, like when you're submitting a form, uploading a file, or creating a new user. This is common with post and put requests. Think of it as the actual package you're shipping. Chapter 3. Unpacking the HTTP response. Alright, you send your request. Now the server does its thing and sends back an HTTP response. Just like the request, it has a specific structure, a status line, headers, and a body. This is the server's way of saying, got it, here's what you asked for, or nope, something went wrong. The status line is crucial. It tells you the HTTP version, a numeric status code, and a human-readable status text. HTTP/1.1200 OK means everything went perfectly. But you might also see 404 not found, a classic. We'll dive deep into status codes later. But for now, know this is your first signal of success or failure. Response headers are similar to request headers, but they provide metadata about the response or the server. Content type tells the browser what kind of data is in the body. HTML, JSON, and image. Server tells you what web server software is running. Set cookie is a big one for state management. This frustrates me because content type is often ignored by junior devs, leading to weird parsing issues. And finally, the response body. This is the good stuff, the actual data you asked for. It could be the HTML for a web page, a JSON object from an API, an image, a video, or even a PDF. If you requested get/index.html, this is where the index.html content will be. It's the payload of the server's reply. Makes sense? Chapter 4. The verbs of the web, HTTP methods. HTTP methods, often called verbs, tell the server what action you want to perform on a resource. The most common are get and post. Get is for retrieving data. It's idempotent, meaning making the same request multiple times has no additional effect. Post is for sending data to create a new resource. Some devs swear by strict RESTful adherence. Others are more pragmatic. Here's my take. Understand the intent. Don't get bogged down by dogma. Still with me? Good, because we've only scratched the surface of how requests and responses work. What if I told you the server's reply isn't just data, but a secret language that dictates how your browser behaves? That's what HTTP status codes are all about, and understanding them is your superpower for debugging the web. Then we have put and delete. Put is used to update an entire resource, replacing it with new data. Delete, as you'd guess, removes a resource. These are also idempotent. If you send the same delete request twice, the resource is still gone after the first, so the second has no new effect. Real talk. Put is often confused with patch, which is for partial updates, but we won't go deep into patch today. Quick side note. There are other methods like head, which requests only the headers without the body, useful for checking if a resource exists or its size without downloading it. Options is for asking a server what methods are supported for a given URL. While less common for beginners, they're part of the full HTTP spec. Wild, right? So much nuance just for asking for data. Chapter 5. Status codes, the server's report card. Okay, let's talk about the server's mood swings, status codes. These 3-digit numbers are incredibly important because they tell you exactly what happened with your request. They're grouped into 5 categories. I know this part is dense. Stick with me. Mastering these saves you so much debugging pain. First, the 2XX codes. Success. 200 OK is the most common, meaning everything is fine. Here's your data. 201 created means a new resource was successfully made, usually after a post. 204 no content means the request was successful, but there's no body to send back. These are the ones you want to see. Then we have 3XX codes. Redirection. 301 moved permanently means the resource has a new, permanent home. 302 found, or 302 moved temporarily. means it's temporarily at a different URL. Your browser automatically follows these. Unpopular opinion. 302 is often overused when 303C other or 307 temporary redirect will be more semantically correct, especially after post. And the dreaded 4XX codes, client errors. This means you, the client, sent a bad request. 400 bad request is generic, something was malformed. 401 unauthorized means you need to authenticate. 403 forbidden means you're authenticated but don't have permission. And of course, the infamous 404 not found. The resource just isn't there. This is probably the most common client-side frustration. Finally, 5XX codes, server errors. This means the server messed up. 500 internal server error is the generic catch-all. 503 service unavailable means the server is temporarily unable to handle the request, often due to maintenance or overload. These are usually out of your control as a client developer, but knowing they exist helps you diagnose issues. Chapter 6, Statelessness and the Magic of Cookies. Here's the deal. HTTP is inherently stateless. This means each request is treated as completely independent. The server doesn't inherently remember anything about previous requests from the same client. This is a fundamental design decision that makes the web scalable, but also creates a challenge. How do you stay logged in? How does your cart remember items? Plot twist, cookies. They were invented to solve this exact problem. When you log in, the server sends a set cookie header in its response. Your browser stores that cookie and sends it back with every subsequent request to that domain. This little piece of data allows the server to identify you and maintain your state. Honestly, cookies are both a genius hack and a privacy nightmare, depending on how you look at it. Chapter 7, HTTP/2 and beyond, the need for speed. For decades, we primarily used HTTP/1.1. It was good, but it had limitations, especially with modern, rich web applications. The biggest bottleneck was head-of-line blocking, where only one request could be processed at a time over a single connection. If one asset was slow, everything behind it got stuck. It was like a single-lane road during rush hour. Enter HTTP/2, released in 2015. This was a game changer. It introduced multiplexing, meaning multiple requests and responses could be sent concurrently over a single TCP connection. It also brought server push, allowing the server to proactively send resources it thinks the client will need. It's like upgrading to a multi-lane, high-speed freeway. And honestly, if your site isn't on HTTP/2 by now, you're leaving performance on the table. And looking ahead, we have HTTP/3, which builds on the QUIC protocol. Instead of TCP, it uses UDP, offering even faster connection establishment and better handling of packet loss, especially on unreliable mobile networks. It's still gaining adoption, but the trend is clear. The web is constantly evolving for speed and efficiency. Go build something with this knowledge. Let's recap. HTTP is the fundamental request-response protocol powering the web, built on a client-server model. Every HTTP request has a method, path, version, headers, and an optional body. Every HTTP response has a status line, code plus text, headers, and an optional body. Status codes 2XX, 3XX for XX, 5XX are the server's way of communicating the outcome. HTTP is stateless, but cookies provide a mechanism to maintain session state. Modern HTTP/2 and HTTP/3 dramatically improve performance over HTTP/1.1 with multiplexing and QUIC. The key takeaways: when debugging, always check the network tab first for HTTP status codes and headers. Choose the correct HTTP method, get, post, put, delete, based on the intended action on a resource. Understand content type headers for both requests and responses to avoid parsing issues. Leverage the power of HTTP/2 and HTTP/3 for faster, more efficient web applications. If this helped you understand something new about the bedrock of the internet, consider supporting the channel. Every bit helps keep these videos free for everyone. Drop a comment with your thoughts or your most frustrating HTTP debugging story.